So, hi everyone, and thank you very much for attending my talk. I'll be talking about fashion, product retrieval, multimodal input, and again, so that's a lot of buzzwords, and let's go for it. First of all, a couple of words about me. So, I'm Ivona. I work at Tautkute, which is a software house based in Poland, Europe. I'm also doing my PhD in computer science and machine learning. I have some background in mathematics, and in my free time, I'm working as a concert photographer. So actually, those two things, concert photography and mathematics, led me to my passion for computer vision and teaching computers how to understand images and what's in them. So during my job at Tautkute, I had a chance to help build a lot of amazing products, most of them from here, from Silicon Valley. So I've helped develop like a passenger counting system, a motion recognition system for autonomous taxi company from California, also smart oven company, smart tire company, a lot of smart things. So yeah, and today I'll be talking about product retrieval. So why do we need that? And as a consumer, why are we interested in product retrieval? A typical use case would be one, it's actually quite happened to me a lot as well. You're just walking in the street or riding a subway, and you see somebody wearing an item you like. It might be bag, shoes, anything else. So you could just approach that person and ask, "Hey buddy, I like your shoes. Where did you buy them?" But that's a bit too awkward for me. What is not awkward is to snap a picture of a stranger and search it in the internet. Yeah, right. So I guess we can just use Google image search. And the thing is, if you search for similar images, you might find other images of people wearing shoes. And those definitely are visually similar images, but they are not what we are looking for. So what comes next is actually a lot of huge companies started doing visual search on a lot better way. And one of the pioneers was Pinterest. They published a couple of very interesting papers about their methods, and they also implemented this solution in their app and website. So we can actually tick a product that you like and search for visually similar ones, and it works really well. Also, more retailers, online shops, everybody started using this visual search. So ASOS, Zalando, some Chinese ones such as Alibaba or AliExpress, everybody starts using that and adding as a feature in their apps. So this is actually very good for consumer because you can just snap a picture, find similar items, and you're good. And why is it gaining so much popularity? One thing is it's very easy. So actually, if you don't even need to have labeled data for the most simple visual search algorithm, you don't even need to train a model. You don't even need a GPU to have like the simplest visual search. What you need is actually just a bunch of images, your database that you already should have, and you get a pre-trained network, preferably on ImageNet. It might be any architecture, ResNet, VGG, Inception, and you just feed all your images for this pre-trained network. You remove the last layer, which has probabilities for ImageNet classes that you don't really care about. And now this second to last layer is actually your vector representation or an embedding in multidimensional space that you can use as an index to search for other vectors in the same multidimensional space. So you choose a distance metric, L1, L2, find the closest vectors, and you have the closest visually similar images. So this works very well because networks pre-trained on ImageNet already learned such features as colors, shapes, and these are actually the features that we are looking for in visual search. But going forward, if you actually have some data and you want to train an even better model, what you can do is you can teach a Siamese network. So to train a Siamese network, you would need to have some positive pairs. So in this case, you would have pictures of the same product, but of different angles, different situations. It might be a picture of a white background, catalog photo, and also another one where somebody is just wearing the product in real life. So then you feed those two images through some CNN architecture. It also doesn't matter so much. It might be pre-trained or not. It depends on the amounts of data that you have. And in the end, you calculate the contrastive loss. So in the case of the pictures of similar product, positive pair, you want this distance to be smaller than a predefined margin. And in the case of negative pair, you want this distance to be larger than a predefined margin. And this is also a fine-tuning parameter that you have to play with to find the best values. Also worth mentioning that those pairs, the negative pairs especially, don't have to be too hard and too easy. If you gave it a negative pair of like shoe and a bag, it might be too easy for model to, it would learn it instantly. But if you give it two hard pairs that are almost similar, but these are of different products, just very similar, it might be difficult to converge. So that's also art in itself, getting those pairs. Kind of similar approach is with triplet networks. Here you don't have pairs, you have triplets. So you start with an anchor image and you get a positive and a negative pair. The difference here is that you don't say anything about the distances, whether they should be smaller or larger than the margin. You just say that the distance between anchor and positive has to be smaller than the distance between anchor and negative one. And what happens during training is that in the multidimensional embedding space, those embeddings of an anchor and positive actually get closer together, and the one of a negative one gets farther. And during inference, again, you just calculate the distances, find the closest vectors, and this is your result. So you might take any picture which is not present in the data set, run it for the network, calculate its embedding, and find the closest one from the database. Now, this is all for the visual search, but sometimes image is not enough. Sometimes you don't have a perfect image. You have image of shoes, but you want them in different color or something in different shape. And this is actually where multimodal search comes into the picture. Because multimodal in this case would mean that our input query is not just visual signal, it's also a text signal. So there are two typical user case scenarios that you would want to do that. And one is a particular when you have an image which is not perfect. So you might want these shoes in black or in leather or anything else. Or you might have a different use case. And this is the case where you can't even have an image which describes the thing correctly. So you might have an image of sneakers that look comfortable and look cheap, but who knows if they're comfortable and cheap. So these are some of the features that are just not translatable to images. And we want them to be defined in natural language. We don't want to be restricted by any predefined features or tags or classes, anything like that. So to do that, actually, me and my colleagues did some research at Tautkute, and we've developed a deep style network which tackled just this problem of multimodal search given some image and text input. And the first network that we've developed a couple of years ago already was this one, where we used classification as an auxiliary task. So we learned multimodal descriptors by doing regular classification. Just an input was image and text. We also used some pre-trained image and text encoders. So for image encoder, you can use ResNet, trained on ImageNet or InceptionNet. It doesn't really matter that much. It just changes the accuracy by a couple of %. And for text, you can use Word2Vec, Glove, or any other text encoding method. On top of that, a couple of fully collected layers that were actually trained. And in the end, where we have the softmax, it's not an actual multimodal descriptor. Is as before the second to last layer, which is the image and text descriptor that we are using for search. Going forward, we improved this method even more by adding a SAMEs component. So right now, having this information in the data set that some of the products are similar, or maybe they are of similar style, or maybe they fit together quite well, we're able to train an even better network for multimodal embeddings. And in this case, we trained on pairs of products, but each of those pairs of products is an image and text itself, so it has two branches already. And the weights are shared between two deep style networks, and the network is optimized with 3 losses. So we have one loss we have contrastive loss, which says whether those two products represented by image and text should be close together or further together in the embedding space. And for each of them, we also have a classification loss, a typical one. So by training this, we were able to improve over some baselines, state of the art at the time, and to get a multimodal retrieval that represents both image features and text features given in some random text. Now, the problem with research is that sometimes you train a great model, you have a perfect accuracy, you improve over baselines, then you implement it in production, and what happens? Users start using that, and they are not happy. They don't like that. So in this example, let's imagine we have a user upload a sneakers picture, and he gets some black shoes in result. We might say, well, it's still shoes, right? The results are not that trash, but the user doesn't get the shoes he's looking for, so he doesn't care if it's sneakers or bags or shirts or whatever. He just did not find those sneakers he was looking for. So the problem is that by just seeing those results, we don't really know what went wrong. It might be the model, it might be the architecture, but in the given database, perhaps there are just no colorful sneakers. Maybe that's the closest that the model was able to get by finding other shoes. There were just no similar ones. So especially in the terms of multimodal search, it's very important to have this component of interpretability and being able to say what we are looking for and what is user being given. So this is where our idea comes into life, is that we want to introduce this interpretable element to our multimodal search. And we're tackling this with generative models. So given an image and text query, we want to create a synthetic image that actually represents both image and text, and then use it in a regular visual search. So here come the GANs. Just a quick question. How many of you here have trained GANs? Okay. How many of you know what GANs are? Okay, that's better. So yeah, GANs are not, well, they are fun to train, but there's a lot of problems while training GANs, stability, mode collapse. So this is really fun, but in a bad way as well. And the problem with regular GANs is that you cannot influence the images that are generated in any way. So you get some synthetic cats, but you cannot just say that you want a cat with blue eyes. In a vanilla GAN version, you just give some random noise and you get a cute cat picture in return. Now, there is a lot of improvements over vanilla GANs. A very popular one is a conditional GAN, where you can condition by label. So if in your data you have some labels, you're able to feed those labels both to the generator and to the discriminator. So by generating images, you feed some noise on one hand, but also you're feeding the label. First, the generator doesn't know anything about the label, so it just takes it. But then discriminator is given real image with label and generated image with label. So even if generator was able to create some good looking images, but they are not corresponding to labels well, then the discriminator wouldn't be fooled. So this is why we are able to actually condition on this label. And we are, for example, here able to generate clothing images that are conditioned on color label. Going further, there's, for example, InfoGAN, and here what's interesting, you can even input not only a categorical variable, but you can give a continuous variable C, which doesn't actually even need to be predefined. It is learned by model during training. It captures some characteristics of the data. So in this case, it's actually trained on celeb dataset, and it learns to associate values of this continuous variable with pose or rotation. And now going forward, there are some interesting models that actually allow you to generate images from text. Attention GAN is especially cool because the authors of this method use attentional models, and this way they are able to create images with some context. So in the case of birds dataset, when you have a text query such as a red bird with blue wings, you don't want this blue wings text part to influence all of your image, just certain parts of that. So it comes naturally, and the authors are getting some promising results on the birds dataset. When we tried to apply this approach to clothing dataset, it appeared that some general concepts look quite good and are quite promising. So in this case, we are giving it a text query, bright long red party dress, and what we see is bright long red party dress. So it's kind of cool. And also they give us some attention maps that show which words trigger which attention maps. Unfortunately, they are not very fine-grained. They don't give a lot of details, but some words, such as bright and red in this case, we are seeing that they are indeed influencing those parts of the image that they should be influencing. Now, from the same authors, there is another very interesting model, StackGAN. And this one is actually a two-stage generative model, which first, from the text query, creates a low-resolution image and then uses that to create a higher resolution one, also conditioned by the same text query. And now the problem with this approach is that in the second stage, it only changes image in some parts that are responsible for creating higher resolution image. So if in first stage you created blue dress, you wouldn't be able to change it in the second stage to something else. So this comes into the question, okay, but how do we make GANs with multi-modal input? We don't only want to have textual input or label input, we want to have it all. So we didn't find any appropriate research on the subject, so we started with our own. It's still work in progress, and we are going to publish it soon, and we don't have a catchy name for that, and researchers supposedly to have a very catchy name for that, so right now I'm just calling it triplet GAN. But the idea here is to leverage on the information about the similarity. So for some time we had ideas that we weren't able to experiment with because there wasn't good data for that, and without the data you're just nothing. So we were very happy when Fashion IQ dataset got released because they have exactly the data what we need, because just having images and text is not enough. And we need those relative captions. We need data in the form of image plus text equals another image. And by having these relative captions, which correspond to differences between images, we are able to do just that. Give an image plus text, we receive a second image. And our idea is to incorporate GANs with triplet loss by having this target image that corresponds to our actual ground truth. So first, image and text are fed from some pre-trained image encoders as usual, and then instead of noise, we feed this concatenated image and text features to generator to create some artificially looking image. Now, the generator would learn to fool the discriminator by giving us some clothing images, which is not yet good enough. We are so adding the triplet loss so that the distances between the generated image and the actual ground truth image is smaller than the distance to some other random image. By adding this loss to the generator during backprop, the generator is able to create images that correspond well to the input image and input caption. So essentially, what we are able to do this way is by having image on the left, which is in some stripes, and user query is in white and has a pocket. We generate the third image that is then later used for general visual search, and we are able to return the closest results. And what is better with this approach than just using text to image is that we are able to capture information present in the image itself. So it's not yet changing some parts of the image, which also quite an interesting idea that we are going to experiment with. It's generating image from scratch, but by having this encoder information in the generator, we're able to capture some important information such as color, such as a person, if it's wearing a clothes, or is it just a clothes on white background, some general shapes or body shapes, etc. So this already gives us some interesting results, and we are also working on improving this method even further. And this would be it. Thank you very much for your attention. I would be very happy to answer any questions.
Hi, great talk. Thank you. Have you considered the use case where somebody needs to revamp their wardrobe? So whatever styles they're looking for are exactly, or to a certain degree, unlike what they currently have.
Okay, so you mean in the case of matching styles, but not the exact items?
So think of it, let's say somebody's entire wardrobe is in blue, green, and red. They don't want any of those anymore.
Okay, so that's a different use case, because then you would have actually you would want items that in the embedding space are not so close, but not so far. So I mean, if you have a good embedding space, that perhaps would be possible, but we haven't played with that.
Okay.
First of all, thanks for the presentation. That was awesome to see. Just curious, like, what are your plans with this? Are you selling it to, the fashion industry and picking up clients, or is there some other plan? And just curious how that's been so far.
Yeah, sure. So right now it's in the research phase, but it's research that I'm doing at Tuplux, and at our company we're actually doing a lot of research before we go to clients. And what we found is that a lot of companies then go to us because they're interested in doing just that. And yeah, we've had some companies actually ask about those methods, because I feel that in fashion industry, there is this FOMO right now that there is a lot of interesting stuff that you can do, especially if you have like vast databases. Everybody's doing visual search, so it's kind of already passé. But there is a lot of more interesting stuff like with multimodal search, like outfit compatibility. And there is a lot of leverage. So yeah, we're hoping to apply that. We've already had some smaller projects on using the multimodal search on client side. But yeah, I'm hoping to see that implemented even more.
So great talk. Where do you see the future or the potential of these kinds of services in the next 5 to 10 years?
Well, so I think that perhaps it would be ever present just everywhere, and easier to use, definitely, because the tool that Pinterest has is quite cool, but the most other tools that I've tried on, they're not so good yet. You just download the app, it looks cool, and then it's not quite what you want. So I think that to be used on a large scale, there is still some room for improvement, and I hope that in next 5 years, this gap would be overcome, and it would be so much easier to use and ever present. Thank you. Okay, so if there are no questions, then thank you again very much, and have a nice one.